All right, let's get started. It is lecture 6. It is Friday, and I have a feeling everybody's geared up for their 3-day weekend coming up, right? And what better way to get started and fired up for a 3-day weekend than to show up at 8 o'clock in the morning to learn statics from your favorite statics professor? That's a party. All right. Okay, so a couple of announcements. I've gotten the attendance grades posted to Blackboard. Homework 2.1 has yet to be graded. I just got my TA's access to the Blackboard course shell yesterday. So they're going to grade homework 2.1 and hopefully 2.2 over the weekend so that when we come back on Wednesday, both of those are graded. I am assigning homework 2.3, but it's not due Monday, it's due Wednesday. Okay, and honestly, it's no longer than any of the other assignments. It's not as if I'm saying, ooh, they have 5 days, I'm going to give them more work. No, it's just any one of the other assignments. So, okay, a couple other announcements. So you should have by now received emails or communication about our Employer Spotlight series. Have you all seen this yet? I would hope so. If not, here's the deal. So in our college, we are hosting a periodic, what we're calling Employer Spotlight Series. The idea is that we will have employers here on campus that will come and make presentations and potentially can develop some connective tissue between them and you, the students, that might turn into co-ops and internships. The first one is on September 7th, which is the Wednesday that we come back next week. I believe they all take place in the Student Center. Lunch is provided, as I understand, at no cost. So, food, that was a topic of discussion this morning. So, just saying. But they're from 11 a.m. to 1 p.m. in the Shockey room. That's in the Student Center. So it's on the second floor of the Student Center. I imagine there'll be posters and placards indicating where you go, and so on and so forth. So, but yeah, if you're interested, contact Tanner Drown. He's our co-op coordinator. His email address is drown12. That's DROWN12. Like I said, the first one is on September 7th. The next one scheduled here is September 21st and then October 5th. Like I think they go every 2 weeks. But I also think that Tanner's working on trying to get a few more employers to fill in some of those gaps. So at a minimum, every other Wednesday, possibly every Wednesday, there might be a new employer. So the DOH is listed first, and then Toyota is coming on the 21st for you mechanicals and whatnot. And so I'll leave it at that. Any questions? All right, one final point. I don't have this on the agenda, but I got to thinking about it. So today what we're going to do is we're going to continue our discussion of IJK notations. That's going to be what we cover in Lecture 6. But Lecture 7, when we come back, is going to begin our formal discussion of 2D equilibrium. And we're going to be solving some 2x2 systems of equations. So that's what we're going to be doing in Lecture 7. So the point I'm making is that on Wednesday, when you come back, I would definitely make sure that you have with you either a scientific calculator or a graphing calculator, something that can solve 2x2 systems. Just about any scientific or graphing calculator can, because we will be doing that in here. And so I will show you in the slides how to do that with a Casio. And then on top of that, I will probably post to Microsoft Teams a series of YouTube videos on how to do that with other calculators. So that way that you have that. I mean, just about any scientific and graphing calculator can do that. But the point I'm making is that if you're using the native calculator on your iPhone and whatnot, I don't think it can. So you need something that's a little bit more robust than that. Sound good? Okay, so what we're going to do is we're going to continue our discussion on vector components, unit vectors, and then IJK notation. I showed you a lot of these slides last time, so I'll probably go through them a little faster this time, just to sort of get to the crux of the lecture, as it were, the examples that we're going to do. But I think by now we understand the concept of adding vectors in a tip-to-tail fashion, that if you have a bunch of vectors all applied at some point A, then what you do is you take those vectors and you slide them such that they're connected in a tip-to-tail fashion, and then the resultant of those vectors goes from beginning to end. Now, that's, I think, fine graphically and trigonometrically if you're looking at this, or looking at a problem that only has 2 vectors. But once you start getting into 3, 4, 5, 6 vectors, that gets kind of cumbersome real quick. And to be clear, we are going to have systems in this class where we would have 4, 5, 6 vectors all meeting at a common point. That is going to happen. A very common example of that is when we start analyzing trusses and we utilize a method called the method of joints. We're going to look at each joint as if it's a particle statics problem, and then each joint is going to have all the members framing into it, all the external loads framing into it. So yeah, there's going to be multiple load components all going into a single point. And so I think my overall point with all this discussion is that adding these graphically in the fashion that we were dealing with in the past couple of homeworks is fine for when you have 2 vectors, but when you have a bunch of them, it starts to get pretty inefficient. And so we need a better way of dealing with it. And so the most natural way of dealing with that is to take a vector and split it up into its x and y components. And so what we're doing is we're taking each vector and representing it with a common basis. And so the idea is that if each vector is split up into its x and y components, I can just add up all the x components, add up all the y components, and I can get the resultant. So it's much more systematic. Now, so that's what we'll ultimately do. Take a vector, split it up into its x and y components, and then just add up all the x components, add up all the y components, and then there's our result. It's a lot easier and a lot faster to add up multiple vectors. Now, in terms of our notation, in order to standardize this in a fashion that we can all recognize and that we can all immediately deal with from a mathematical perspective, what we're going to do is break out the definition of a unit vector. So if we remember, vectors are mathematical objects that contain magnitude and direction, right? So a vector is going to have some magnitude, we'll call it f, and some orientation theta. Well, if I factor out the magnitude, what I'm left with is a vector that has a magnitude of 1 and some orientation. And we have a name for that, we call it a unit vector. So the idea of a unit vector is it has a magnitude of 1, so because it has a magnitude of 1, its purpose is really just to convey direction, okay? And unit vectors are going to become very, very important down the road. Now, our most common unit vectors, or our most essential unit vectors, are the unit vectors along the cardinal directions, along the x-axis, along the y-axis, and along the z-axis. Because if I take one of these unit vectors and multiply it by some magnitude, then that's an easy way of expressing how much magnitude a vector has along the x-axis, how much magnitude along the y, how much magnitude along the z. And so we term those IJK, and I think we've tended to settle on the notation of IJK because I think, I mentioned this on Wednesday. I said, how many of you have ever seen IJK? And like half the people raise their hand. It's a common way of expressing vectors, such that if I just mention IJK, everybody knows what I'm talking about. So that's sort of why we use those terms. So the I vector is the unit vector along the x-axis. So it is a vector that points along the positive x-axis, and it has a magnitude of 1. The J vector, again, magnitude of 1 along the y-axis. K, magnitude of 1 along the z-axis. They always point in the positive direction. So if you take these vectors and multiply them by a negative number, that just tells you that they're pointing along the negative x-axis. That's why the vectors retain their direction along the positive direction. Now, for now, what we're going to do is we're just going to deal with 2D problems, where we're going to deal with just problems that have I and J. Later on, we'll add the K vector. But that's another advantage of expressing vectors in IJK notation is that if you are comfortable with dealing with problems in 2 dimensions, 3 dimensions it's no more computationally difficult. They're longer, and the problems just have a few more steps, but they're not more complicated. They're not harder. So I think that's one of the other advantages of dealing with things in this fashion. So the way that we'll express vectors in their components is, again, we'll say a vector equals some vector along the x-axis plus some vector along the y-axis. But the way that we'll denote that is we'll say some magnitude along the x-axis times I plus some magnitude along the y-axis times j. And then later on, some magnitude along the z-axis times k. Now, in order to actually do the math, what we can do is recognize that this is just a right triangle, right? So if we understand this angle, this magnitude is the hypotenuse times the cosine, or times the sine. That's what this magnitude is. And this magnitude is the hypotenuse times the cosine. That's pretty easy. So we can express this, pretty easily using some fundamental trig functions. The only thing I will say is please don't do a homework assignment, and let's say you have a problem where the angle is measured from the y-axis and you just plug and chug into this formula because that was the formula Dr. Mike showed on that one slide, and it's boxed and it's yellow, so that's obviously the right formula. Just make sure that whenever you're using this, that the angles are measured from the x-axis. Remember, when you're dealing with rectangular versus polar coordinates, that term theta assumes that the angle is measured from the x-axis. That's why we associate the cosine with x and the sine with y, because the angles measure from the x-axis. If the angle's measured from the y-axis, you either need to take 90 minus that angle, or you need to flip the functions. So, everybody okay with that? So we're going to have two problems. The first problem is very, very simple. We're just going to take a vector and express it in IJ notation, and then we're going to add three vectors, and we're going to do it very systematically. And I think you're going to find that this is a lot easier maybe than some of the graphical and trigonometric approaches that we did earlier. I think it's important to do those approaches so that it's like, if you understand that, you can certainly understand this. So again, it's sort of like stretching the abilities a little bit so that we can get to the good stuff. Okay, so we're going to start off with a very basic problem. I have a vector here, and I want to express it in IJ notation. Okay, now I tend to keep these pretty simple in my computations. So the first thing I want to do is I just want to make some basic observations. Bless you. All right, so I have 800 newtons, and it is oriented at an angle of 35 degrees. Okay, so let's ask a couple basic questions. Now, is this angle referenced from the horizontal axis as opposed to the vertical axis? Yes, right? Now, I'm sure that some of you are saying, well, wait a minute, it needs to be over here, right? Well, that's true if you're trying to be, such a stickler, on the trig definition that you might have learned in Math 122 or Math 132 or what have you. But I tend to think that context is a little easier to deal with from an engineering perspective. And what I mean by that is this. So if I look at this vector, okay, is the y component of this vector going to be positive or negative? Positive. It's pointing upwards. Is the x component going to be positive or negative? Negative. It's negative because it's pointing to the left. So let's just ensure that we've got that context in our head, and I think everything else kind of works out pretty well. So what do I mean by that? So what I'm going to do is I'm going to take this vector. Oh, my string got all tied up. There we go. I'm going to take this vector, and I'm going to draw it over here. This is 800 newtons. And I'm going to sort of draw out my right triangle. So here's my right triangle. Oh, sorry, 35 degrees. And so that's 35 degrees. Okay? Now, what I've got here is I've got some, we'll call this magnitude along the x-axis right here, magnitude along the y-axis right here. So what I'm going to do is I'm going to say, in order to compute, let's say, the magnitude along the x-axis, I'm going to take the magnitude and I'm going to multiply it by the cosine of that angle. Okay? And so when I do that, I'm going to get 800 newtons times the cosine of 35 degrees. And tell me what you get for this. Again, I know it's going to be negative. I understand that. Just we'll get to that here in a second. But just what's 800 times the cosine of 35? Yeah, six. Did you say 655.3?
Oh, yeah.
Is that, I couldn't hear you. Is that that's right? Okay. And that's newtons. Do I have a second on that? Okay. So for the y component, we're going to say F times the sine of that angle, which is 800 newtons times the sine of 35 degrees. And so what do we get for this? 458.86. Do I have a second? Okay, so if we're expressing this in vector notation, the answer then would be F. Again, make sure you put your little arrow there. Oh man, I'm moving that because there's little things in front of the screen. That's better. Maybe I need to contact facilities about those things, those little wires. Is negative 655.32 newtons times I plus 458.86 newtons times J. And that's it. Now, I'll go ahead and tell you, sometimes what I will do is this in class. So sometimes I'll write it like this. I'll say note. I'll say F is negative 655.32 I plus 458.86 J. But then I'll put off to the side expressed in newtons or something like that. So in other words, sometimes I don't feel like writing the Newton symbol over and over and over again, so I'll stick it on the outside. But I do think it's important to indicate for the vectors that we're dealing with what are the units, because I think that by doing that, especially later when we start getting into 3D land, it will help you track the steps that you're dealing with in your problems. So as an example, one of the things that we're going to have to do in 3 dimensions is we're going to have to express forces in 3 dimensions. And the way that we do that is we first develop a distance vector, then we take that distance vector and we turn it into a unit vector, and then we take that unit vector and we turn it into a force vector. So the idea is that the first step, the vector will be expressed in meters or feet, some distance. The next step, it won't be expressed in anything, it won't have any units. Then it will be expressed in newtons or pounds. So I do think tracking those units is going to be kind of important later, just to ensure that you're on the right track with some of these problems that are no more difficult, but they are a little bit longer. Okay, does that make sense? All right, so far so good? This isn't so bad, right? So now let's take this problem, let's ratchet it up a little bit, okay? I think this will work. Let's see. Nope, that won't work. All right, so this is our next problem that we're going to deal with. So this one is a little bit more challenging than the one that we did last time, okay? This one, we've got 3 vectors, and we're going to sum those up. Now, I can tell you right now that if we were going to take these vectors and deal with them in a law of sines, law of cosines fashion, we could do it, but it would make this problem just a lot longer and a lot harder. So we're going to utilize this IJ notation. And remember, the resultant of a vector is just summing them up, okay? So when you take vectors and you stack them on a tip-to-tail fashion, all you're doing is adding. Now here's what's different. Notice how I didn't give you any angles, okay? So for example, if we look at this 29-pound vector, I didn't say what angle it's measured, from the x-axis. Instead, I'm giving you these dimensions, these 80 inches to 84 inches. This is very common in engineering land, that maybe you're not given the angle, maybe you're given the dimensions about which that vector is acting, so you need to determine the angles, okay? So that's very common. Okay? Now, our approach to this is going to be much more systematic than it has been in the past. What we're going to do is we're going to take each one of these vectors and we're going to express them in IJ notation and then add them up in that fashion. So I think the first thing I want to do is I want to name these vectors. So let's see. Let's call this vector A. Let's call this vector here B. Let's call this vector here C, just so we have a common naming system, okay? And we'll take each vector and we'll express them in IJ notation. Let's start off with vector A. So here's vector A. We have here's 29 pounds. There's that origin point, okay? And what we're given is something about like that. And we know that this is 80 inches. I can do better than that. And this is 84 inches. And so what we kind of need to figure out is this angle. Okay? So the first thing I'm going to do is I'm going to figure out this angle. And I'm going to do that based off recognizing that the tangent of that angle is going to be that. Is that a fair statement? Opposite over adjacent? So if I want to determine that angle, I take the inverse tangent of 80 over 84. And what is that? We'll say to like 2 decimal places just to make sure we're all sort of getting the same values. $43.60. Have a second? Okay, good. All right. So in this regard, what I can do is I can say fx equals f cosine theta a, which is 29. By the way, I'll show you something. What are the units for 29 pounds? If you happen to be reviewing calculations and you see this, like the hashtag symbol on telephones, that used to be the pound symbol. So it's every now and then you will see engineers refer to pounds with that sort of shorthand. So 29 pounds. Well, yeah. So if you ever see the hashtag symbol in a calc like that, that's what that's for. Okay, cosine 43.60 degrees. So what do we got for that? Well, we'll keep it simple. We'll just if you're tracking your decimals, I would imagine this probably comes out to like an exact figure. Yes.
On the graph there, like what angle did you just find?
Oh, okay, that's a great question. What I was finding was this angle right here. This one right there. You don't seem convinced.
Yeah, I just don't see why you took those numbers.
So, okay. Let's look at this. Okay, that's fine. Let's look at this triangle. Okay. So, all right. So I'm going to erase this part real quick.
Oh wait, no, actually, I think I did.
Yeah. So if I look at this triangle right here, like that triangle right there, okay, that's 80 inches, that's 84 inches, and I'm finding that angle. So the tangent of that angle is opposite over adjacent. Don't hesitate if you ever have a question like that, please. I guarantee you weren't the only one who probably asked that. Is everybody else good with that? Everybody good? Okay, this is good stuff. I like that. So So what do we get for this? And if you're tracking your decimals, it probably comes out to a nice even number. 20, say it again?
21.00098.
Yeah. So I'll tell you why that happens. So we'll say 21.0 pounds. If you actually do the math and actually track the decimals, it ends up being exactly 21. The reason why is because this 80-84 triangle, it's actually kind of a perfect triangle. It's what's called a Pythagorean triple. So a Pythagorean triple is an example of that is a 3-4-5 triangle. You all know what I'm talking about there. So if you have a right triangle that's one leg is 4 and the other leg is 3, if you find the length of the hypotenuse is exactly 5, you know what I'm talking about? So 3, 4, 5s, 5, 12, 13, 8, 15, 17. And actually a lot of these triangles in this problem are like that. So what happens is the x and y components are probably going to come out to exactly even figures. The reason you're getting 21.0000 is that you're probably using 43.6 and not 43.6. It's your, whatever. So, sound good? So I wanted to just forewarn you, not all problems are going to be that pretty. I just want to make sure that you're aware of why this one is. Okay, Fy. So Fy is Fy times the sine, which is and what do we get for that? And it again should also be a whole number. $20. Do I have a second? Okay, good. So therefore, vector A is 21 pounds times I plus 20 pounds times J. And you will commonly hear me refer to this as I hat, J hat, and K hat, because usually for your unit, your essential vectors, you usually write those with a little hat over them. So far so good? Shouldn't be all too bad. Okay, so now we're going to take the other two vectors and do the exact same thing. Okay, so I will try and not do too much scrolling up and down, but I'll tell you what I will do. I am going to sort of like box this one so that when we start referring to vectors later, it's sort of easier to find it. Okay, so let's deal with vector B. So vector B looks something, I don't know, like that. Its magnitude is what? 50 pounds. And we know this dimension and this dimension. Okay, let me scroll up a little bit. All right, so here's the vector, right? We're looking at this vector here. So the y dimension is what, this 96 inches, and the horizontal dimension is this 28 inches. Does everybody see that? So what we'll do is we'll do the same thing. So we'll say this is 28 inches, this is 96 inches, and what we're after is this angle right there. And so the tangent of that angle is 96 inches over 28 inches. Is that fair? So therefore, is that, and what do we get for that? We'll say 2 decimal places. Wait, did I say 96 or 90? What did I? Yeah, 96, sorry.
73.74.
Do I have a second on that? All right. So therefore, fx and fy. So fx and fy, we have f times the cosine This is F times the sine. So let's get those magnitudes. So this is 50 pounds. All right, so what do we got for these? 14 even? Do I have a second? And what about this one?
48.
Second? I think I heard a couple people say that, so I think we're good on that. So, is this right? Right, hold on. Be consistent. Is that right? You're shaking your head no. Why?
Your 14 would be negative, right?
Exactly right. 100% right. 14's negative, and 14's negative because it's pointing leftward along the left x-axis. So it's negative 14, positive 48. Okay? Does that make sense? All right. So let's box that one, make sure we have that easily referenced. All right. Okay. Next one. In a weird way, I will tell you, notice how this is starting to get kind of rote. It's kind of the same thing over and over again. If it gets boring, I feel like I'm doing my job, because if you understand this well and it's just the same thing over and over again, then that means you understand it. So, yay. That's kind of the point. So it kind of, in a weird way, I'm sort of hoping that this gets a little boring, because once it gets that way, that means you're golden. Okay, let me scroll up a little bit. Again, I'm going to try and keep the scrolling to a minimum. I know that's kind of hard to keep track of. So we have vector C. It has a magnitude of 51 pounds, and then the vertical component is 90 inches. This is 48 inches. Okay, 90 and 48. And so, remember, we're always interested in finding the angle from the horizontal. Okay, so that's the angle that we're interested in. So, from the horizontal axis, we need this angle. I would say that the tangent of this angle (90/48). Did I do that right? I think I did. The opposite over adjacent, right? So equals. Make sure that whatever angle that you're computing is always from the horizontal. Okay? You have a question?
No.
Oh, no. Don't hesitate if you got a question. Please speak up. Again, my philosophy is, whether it's scholarship, loans, out of pocket, or your parents, somebody's putting cash money for you to be in here. So if you got a question, you ask. Okay? All right. What do we got for this? 61.93. Do I have a second? So therefore, fx is f times the cosine of that angle. Yeah, 51 pounds, right? Not 50. Yeah, 51 pounds. So what do we got for this? Let's do X first. 24 and then FY. All right, 5 seconds on those. Okay. So therefore, by the way, I don't know if I've said this, but if you ever see me draw 3 dots like that, that means therefore. So I think I've said that. I do that a lot, so. So that's 21 and 45, right? 24. Oh, yeah, 24. Sorry. But that's 24 and 45, right? Negative 45, exactly. Like I had this big point. It's like, yeah, you got the number wrong on 1. Okay, so now we've taken each of our 3 vectors and we've expressed them in a common notation. And I also think one of the beauties of this notation is that I think it's a lot easier to visually or mentally picture what the vector looks like without the picture. You know, in other words, if I'm looking at this vector B, negative 14I plus 48J, okay, so here's a coordinate system, a little bit this way, a lot that way, vector goes about like that. I can see that in my head, right? I can actually figure that out mentally without drawing a picture. It's one of the beauties of this notation. Okay, so we've got each of our 3 vectors. We are in the process of determining a resultant. Instead of the tip-to-tail addition, we're going to recognize that the resultant is just the sum of vectors. So that's another thing. This notation makes it really easy to sum vectors. So how do we do that? The resultant is the sum of the components. I just said this. Have you all seen this notation before? If you haven't, if you ever see the Greek letter sigma, like I kind of draw it like this, but textbooks maybe sort of draw it like that. I'm sure it's on the occasional fraternity and sorority hoodie here at Marshall. But in mathematics, the capital Greek letter sigma is used to represent summations. So if you ever see the capital Greek letter pi, those are products. That notation isn't as common, though. I mean, you use it, but you don't see it all that often. Okay, so just food for thought. Lowercase sigma tends to represent stresses and whatnot. You learn all about that next semester in 216. Okay, all right. So the way I like to do this is I like to add vectors the way that I learned how to add numbers in like 3rd grade. So I will say A, B, C equals, and then I'll just rewrite all my vectors. So 21, negative 14, 24, plus, bless you. Okay, one thing I'll mention as I'm writing this out, because I thought about this, I have chosen to write these vectors in a very specific way. And this is just like my way, like Greg's way of doing it. But if you'll notice, like if we look at vector C, I didn't say 24I minus 45J. I said 24I plus, and then parentheses, negative 45. I've written it this way because I wanted to keep all of the signs inside the parentheses. And I do this just because for me, when I'm adding the vectors up, I can just look inside the parentheses and add those numbers together, and it's a little easier to deal with visually. But you don't have to do that. That's sort of my way of doing it. All right. So if we want to determine the resultant, it's just the sum of these components. And then what do we have? So let's deal with the x components. So 21 minus 14, that's 7. 7 and 24 makes 31. Did I do that right? So 31 I plus, and then what do we have for here? So 20 and 48 is 68. 68 minus 45 is 23. I did that right? Could somebody check me on that? Okay. There we go. So if you want, what is one of the answers? Here's one of the answers. What is the resultant vector? The resultant vector is 31 pounds times I plus 23 pounds times J. That's one of your answers right there. So if you want a physical understanding of what that means, here's the idea, okay? I have a system that has 3 forces on it. What I could do is replace all 3 of those forces with just one force. That one force is the resultant. So I could delete A, delete B, delete C, and replace it with R. R just being 31 pounds along the x-axis and 23 pounds along the y-axis. And that would be statically equivalent. There's that word static, so I think that's kind of an important word this semester. That would be statically equivalent to those 3 forces. So we are resolving those 3 forces into just one. And that would be our resultant. Now, that is the resultant vector, okay? What if I wanted to take this vector and determine its magnitude and directions? Let's start off with magnitude. What do you think would be an easy way of determining the magnitude of this vector? The Pythagorean theorem, that's 100% right. I know the magnitude along the x-axis, I know the magnitude along the y-axis, but what about the magnitude of the whole vector? Well, it's a triangle. Here's how much along the x, here's how much along the y. I want the length of the whole thing. Pythagorean theorem. Pretty simple. So if I want the magnitude, so the magnitude of R, or just R, we can do that or compute that using Pythagorean theorem, right? So remember, the magnitude of R, we can represent with those absolute values, where I can just write R. And it's just the x component plus the y component squared. So R equals, in this case, 31 pounds squared plus 23 pounds squared. So what does R equal? This one is not going to be a pretty number, so we'll say like 2 decimal places. Say it again. 41.77. Do I have a second on that?
I got 38.67.
See, that's what I got. I got 38.6. Maybe check the whether you squared everything, whether it's 31 and 23.
I did 28.
Oh, that'll do it. Yeah. Yeah. Everybody good? Now that's the magnitude. What about the direction? Well, let me ask you this. What quadrant is this vector in? Is it in 1, 2, 3, or 4? 1, right? It's positive x and positive y. In other words, the vector looks something like this. So let's take a look at what the vector looks like. Here's the point of application. There's the vector. So now we know the magnitude is 38.6 pounds. We know this part is 31 pounds. We know this part is 23 pounds. And what we're after maybe is this angle, theta r. Well, at this point, we should be pretty comfortable with doing that, right? I mean, we know that theta r, well, we know this. We know that the tangent, call my eraser. We know that the tangent of theta r is is RY over RX. Or in this case, 23 pounds over 31 pounds. Right? So we can say then that theta R is the inverse tangent of that. What do we get? 36.57. Do I have a second on that? Okay. So therefore, another way of expressing R could be 38.6 pounds at an angle of 36.57 degrees. So we'll do this. Let me stop for a sec. What do you think? Is this bad? Hopefully this is pretty simple, right? So, any questions about the concept? All right, a couple things. So number one, I'm going to give you a problem just like this. So you got a system of vectors. What I want from the answer at the end of this problem is I want this and this. I want to know what is the resultant vector in IJ notation, and I want to know what the magnitude and direction of that vector is. Okay? If you know how to do this, that should be a breeze. With that, I'm going to pull up the QR code in case anybody came in late. With that, I'm going to let you out 2 minutes early. Hope you have a fun 3-day weekend. I know my man in the Hawaiian shirt's ready for his 3-day weekend. So that's all I got. I will see you all on Wednesday.